and the amount of boost to its velocity was equivalent to a jet carrying 5 billion tons of matter that would give it a recoil.
Particles far larger than ordinary sunlight-scattering dust are being released into space by 3I Atlas, forming a structure that should not remain intact under solar radiation pressure. Images show a long, razor-thin antitail pointing directly toward the sun, stretching hundreds of thousands of kilometers while remaining tightly collimated. This is not the diffuse, fragile glow produced by microscopic grains typically liberated from comets as they warm. Small dust particles should be rapidly pushed outward and dispersed by sunlight, yet the material associated with 3I Atlas holds together, maintains a narrow geometry, and persists over extreme distances. To remain visible and coherent under these conditions, the particles must be far larger than ordinary cometary dust. Larger particles feel much less force from sunlight relative to their mass, allowing them to move outward without being blown apart. They can maintain a narrow structure and remain visible over vast distances. But this immediately introduces a deeper problem. Known comets do not preferentially shed such large particles in a way that dominates their visible appearance. Their dust populations are typically skewed toward much smaller grains. The particle size distribution inferred from 3I Atlas does not merely stretch the boundaries of comet models, it sits outside them. The object behaves as though its mass loss is governed by an unfamiliar regime, one that standard explanations struggle to reproduce without invoking special conditions. This dominance of large particles is not a minor technical footnote. It changes how the object interacts with sunlight, how its jets evolve, and how its behavior should be interpreted. Loeb presents this not as a speculative flourish, but as a physical anomaly. If the observed structure is real and persistent, then 3I Atlas is not simply an exaggerated version of a comet we already understand. It is something that forces a reassessment of assumptions that normally work remarkably well. The optical strangeness of 3I Atlas is not where the questions end. Another unusual aspect emerges when the object is examined not with cameras but with radio telescopes. On July 2, 2025, 3I Atlas was observed using the Allen Telescope Array across a wide frequency range from 1 to 9 gigahertz. This kind of observation casts a broad net sensitive to many forms of radio emission, natural and otherwise. The initial results were overwhelming. Roughly 74 million narrowband hits were recorded, a reminder of how saturated the radio sky is with interference from Earth and space alike. As the data were cleaned, interference stripped away layer by layer, the numbers collapsed dramatically. After filtering, only about 2 million hits remained. Further filtering based on sky position reduced the dataset to just 211 signals that could plausibly be associated with the object's location. None of them showed any credible evidence of a signal moving with 3I Atlas. In radio astronomy, silence is not empty, it is informative. The absence of a detectable signal places limits on what the object can be doing. From this non-detection, researchers derived an upper limit on the object's isotropic radiated power. In the observed frequency range, 3I Atlas could not be emitting more than roughly 10 to 110 watts in radio energy. That is an extraordinarily low level, especially when compared to even modest human transmitters. Independent observations from the Green Bank telescope pushed this limit down even further, to about 0.1 watt at similar frequencies. These numbers do not imply anything exotic on their own, but they sharply constrain interpretations. Whatever 3I Atlas is, it is not radiating detectable radio power in a way that tracks with its motion. At the same time, radio silence does not imply physical smallness. A separate line of investigation combined measurements of non-gravitational acceleration with estimates of mass loss from the object. When comets or comet-like bodies outgas, the recoil can subtly alter their trajectories. By measuring these deviations and estimating how much material must be escaping to produce them, researchers can infer the object's size. A recent preprint using this approach suggests that the nucleus of 3I Atlas is on the order of 1 kilometer in diameter. This is not a tiny fragment, it is a substantial body. The estimate aligns broadly with earlier predictions, but it comes with significant uncertainties. Non-gravitational accelerations can be difficult to measure precisely. Mass loss rates depend on assumptions about particle size and velocity, and the true speeds of the ejected material remain unknown. Even so, the emerging picture is internally consistent, a kilometer-scale object shedding unusually large particles, producing a narrow sunward jet, and remaining radio quiet at extremely low power levels. As these observations accumulated, Loeb placed them within a broader framework of anomalies associated with 3I Atlas. The persistent sunward jet is not an isolated oddity. It sits among a growing list of statistically unlikely features. One of the most striking involves the object's trajectory. 3I Atlas follows a retrograde orbit that is closely aligned with the plane of the solar system's ecliptic. For an interstellar object arriving from a random direction in space, such alignment is improbable. It does not violate any laws of motion, but it is the kind of coincidence that raises eyebrows when stacked alongside others. The timing of the object's passage adds to this unease. Its approach and departure place it at specific distances from planets like Mars and Jupiter that appear unusually well-timed relative to predicted encounters. After perihelion, its future interaction with Jupiter occurs near the planet's Hill radius, the region where Jupiter's gravitational influence dominates. Each of these alignments can be dismissed individually as chance. Together, they begin to form a pattern that demands attention. The behavior of the sunward jet itself deepens the puzzle. Both before and after perihelion, the jet appears tightly collimated, far longer than it is wide, and remarkably stable. This alone would be noteworthy, but perihelion introduces a critical complication. As 3I Atlas passed closest to the Sun, its trajectory was gravitationally deflected by about 16 degrees. In orbital mechanics, such a deflection is substantial. If a jet were anchored to a fixed location on the object's surface, its apparent orientation relative to the Sun should have changed. Yet observations suggest that the jet remained sunward on both sides of perihelion. This persistence imposes strict geometric constraints. For the jet to remain aligned with the Sun before and after a significant deflection, the object's rotation axis must be oriented in a very specific way. Observations indicate that the axis was nearly aligned with the Sun's direction prior to perihelion. The small wobble detected in the jet further implies that its source lies extremely close to the rotational pole. If the jet originated from a region far from the pole, rotation would cause it to sweep across a wide angle, producing a much larger oscillation than what is observed. These constraints compound one another. The probability of a randomly oriented interstellar object having its rotation axis aligned with the Sun, its jet source located near the pole, and that configuration persisting across a 16-degree orbital deflection is low. Again, not impossible, but increasingly fine-tuned. The geometry becomes even harder to reconcile when illumination is considered. The jet appears to activate only when its source region is sunlit, yet other regions do not produce comparable activity. This implies an unexpected degree of thermal insulation or selective activation, unlike the widespread outgassing typically seen in comets near perihelion. Composition introduces another layer of anomaly. Spectroscopic observations suggest gas ratios that differ markedly from those of known comets, including unusually high nickel relative to iron and a surprisingly low water fraction. Typical comets are dominated by water ice, which drives much of their activity as they approach the Sun. A plume containing only a small percentage of water by mass challenges conventional models of cometary composition and raises questions about the object's origin and internal structure. Physical and optical properties add further weight. The object exhibits extreme polarization behavior in its coma, unlike what is seen in most comets. Near perihelion, it brightened faster than any known comet and displayed color properties that made it appear bluer than the Sun. Each of these observations sits at the edge of known distributions. None breaks physics, but each pushes against the boundaries of what is commonly observed. The central anomaly tying many of these threads together remains the sunward jet that refused to turn. Maintaining such a jet across perihelion, despite a significant gravitational deflection, is not just a visual curiosity, it is a dynamical constraint. Any explanation for 3I Atlas must reproduce this behavior without relying on an accumulation of coincidences so extreme that they become implausible. That is the challenge Loeb emphasizes. The issue is not that nature cannot produce rare events, but that at some point rarity demands scrutiny. Viewed as a whole, 3I Atlas presents a convergence of improbabilities. Unusual particle sizes, extreme collimation, radio silence, specific geometric alignments, anomalous composition, and persistent jet behavior all point in the same direction. This object does not behave like a standard comet. The question is not whether natural explanations exist in principle, but whether they remain convincing when every constraint is taken seriously and simultaneously. As the object recedes from the sun and fades from view, the opportunity for direct observation narrows. What remains are data, models, and unresolved tensions between expectation and observation. 3I Atlas does not offer easy answers. Instead, it forces a confrontation with how willing science should be to accept coincidence when patterns begin to accumulate. In the end, the significance of 3I Atlas may not lie in what it ultimately turns out to be, but in what it reveals about the limits of current frameworks. Interstellar objects are rare messengers, carrying with them information from environments far beyond the solar system. When one of them behaves in ways that strain familiar explanations, it is a reminder that the universe is under no obligation to conform to our most comfortable models. Whether 3I Atlas represents an extreme natural outlier or something that demands a deeper rethink, its passage leaves behind a lingering unease, the kind that quietly reshapes how future discoveries will be interpreted.